Hey guys, I'm your host Subhra. Welcome to your favorite channel, Subhra the Geek. So, guys, as you know, who am I and what are my educational qualifications and all, and these are the series which I have planned along with my great friend Debayan from industry to bring you to guys how industry wants and what are the things we can experience in industry and what are the things we need for the industry and we need to be ready for the industry. So guys, if you're new to my channel, please hit the subscribe button and the bell notification icon beside it so that you get notified each and every time we post a new video. And please share it with your friends who can utilize this thing and get a good proper job in the industry, which Harvard has classified as the sexiest job of 21st century. A Harvard Business School, to be very specific. So today we are gonna be talking about the fundamental building blocks of linear algebra, mainly vectors and vector spaces. If you are new to my channel, please do subscribe, please. And if you like the educational content we will be pushing in the coming few months, don't forget to hit the bell icon beside it so that you can get updated whenever we publish a new tutorial video in any one of our three educational series. Link will be provided as soon as all the videos are done. So guys, next will be Debayan, who will be taking you through each and everything. And guys, moreover, we have our exclusive Discord server where you can throw us any questions, any queries which you face during your journey, and I and Debayan will be very happy to help you and solve your queries. So guys, without further ado, I am your host Shubro, and
This is Debayan.
so let's start, shall we?
Hi guys, this is Debayan. So today we're going to be talking about vectors and vector spaces and in linear algebra. This is a pretty important topic, and we are going to be covering the basic fundamental aspects of it. We're going to be understanding what these things are and how they are exactly important in sort of forming the foundations of our learning for data science and machine learning concepts. So let's start with a very simple question, right? So how do we represent information, any kind of information regarding aspects and angles of a single measurable quantity? If that question seems way too complicated for you, let me bring it down to a physical kind of scenario that you guys can relate to, right? So we want to talk about a variable. Let's say a variable. We want to talk about a concept or an idea, like a hypothetical idea called not so hypothetical, called a student's academic performance, right? Let's say we want to measure this, we want to put a number to this, we want to quantify this. So how do we go about doing this, right? What do you think, Shubha?
So I think we can say like a student gets 90 out of 100. So that's for a
Yeah,
single student,
sure,
no?
sure, yeah, all of us get 90 out of 100, yeah.
Like pun intended, no, the man?
Mm-hmm. So yeah, coming
So
back to the topic, yeah.
75 out of 100. Let's go for that.
That's realistic, yeah.
Yeah.
Even though, yeah, 75 out of 100, right? So that's that's a marks, right? And that should be in, let's say, in subject like chemistry.
Mathematics.
Yeah, like chemistry. I think many of us find chemistry a bit intimidating at times. So let's say chemistry,
Like that's
right?
my
Then
biggest fear of all the subjects, and you picked chemistry. Very good, the man.
yeah, like yeah, that's how I wrote. Yeah. So okay, 75 out of 100. So that's in chemistry. Let's say you got around let's say 87 out of 100 in physics.
Physics.
Yeah, like, reasonable. If you're good at it, we are supposed to be. We are in this series, and at the end of the series, I think you would expect that you would get a better marks in your exams, at least. So, and we are getting something around like 91 out of 100 for your maths exam,
Mathematics.
which we are going to
That's
study.
very realistic, Debayan. That's very
Yeah,
realistic.
sure. Yeah, at least for our for our guys out there who are listening to you watching this, you will be.
Yeah,
At least you
after
can.
the series. Yeah.
Yeah, like, yeah. Let's not make it a running joke. Yeah. So these are the some aspects of a student's academic performance that you could use subjects, right, and how much marks they got in that in a particular examination for that subject. So we could write this as so this is 75%, right? This is 87%, right? And this is 91%, right? So we could say, right? We could say performance, if that's a thing. Performance
Debayan,
variable.
can you use not so thick fonts? Can you use a little bit like thinner fonts?
Yeah,
Yeah, that
yeah.
would be
Let's increase that. I think no, it should be. Is it okay now?
much more thinner. Would be much easier for us to
Okay.
read.
How about
Yeah,
no performance, right? So let's say performance is equal to 75%, 87%, 91%, right? So you
yeah.
could say, okay, let's say for for student A, his performance is 75, 87, 91, right? And you say it in that specific, like order, that specific order. So this one is chemistry, this one is physics, and this one is maths, right? And this is how you might talk about that student's particular academic performance. We could also like it like this. It's like 75, 87, 91, right? And we call this, you could write it like this is just a notation, right? There is no, it's not a fancy way of writing things. It's just something a physicist and same guys have sort of agreed on to write it like this. So you could also write it like 75, 87, 91. It means the same. It sort of effectively represents the same quantity, same thing. So you could write it like this. This way of writing things is how we call a vector, right? So this set of numbers form a three-dimensional vector, right? So let's break it up. So we have performance P, right? Let's call it performance P, and we say it's 75, 87, 91, and this is for student 1, right? And we're gonna represent that whole quantity as student 1 as a subscript. You can write it any way possible, it doesn't matter. I'm just writing it on a shorthand notation so that you guys can understand. 75, 87, 91. That's our agreed upon notation of representing that whole statement. That so student A has got 75 in chemistry, 87 in physics, and 91 in mathematics. This simple statement, this simple equation, this compressed expression sort of tells that statement in a short go, right? That's how we write notation. That's why it's called sort of like shortening what we're trying to say and trying to say more in few words, in few sentences, in few expressions, right? So this this representation is what we called a vector representation, right? And this has three elements of it, or what you would call aspects of it. or what you would call properties of it, and you might as well call dimensions of the quantity, right? These are all sort of something you can use in colloquial terms, but the meaning what it refers to is the same. These are parts of the same idea of a student's performance, and we represented them as separate quantities. When we group it together and write it as one, like in one notation like this, we call it a vector notation, and it's a three-dimensional vector notation, and it is of the quantity called performance, right? So let's say this is student, like just for one student. How do
So
we do this
Debayan,
for? Yeah.
let me ask you. So we can represent the quantity for a single student, but in a class there may be, say for example, 10 students.
Mm-hmm.
So can we generalize it, or can we represent it for like 10 students at a go?
Yeah, so we can do that, as well. So this is for one student, right? And we are
Yeah.
assuming that in a class of n is equal to 10, right? So there are 10 students, n students, right? So each of them will have p of s1, p of, like s1, p of s2, p of s3, keeping in mind this will go up till s10, keeping in mind, and all of them mean this thing. This is a shorthand form, right, in saying the academic performance of student 1, student 2, student 3, and so on up till student 10, right? This is what we want to write down, but in one compressed notation. How do we write that, right? So we create something called a matrix, which almost look like a table, right? We say it like this. So this is the performance of the whole class, right? So this is my way of saying performance of the whole class, right? You could write it on the top as well. It doesn't matter much, but it means the same thing. We have decided on what we want to call it, right? So we call it like this. We create a whole table. We write marks. Let's say for student 1 we know 75, 87. Is it 87? Yeah, 87 and
91.
91, right? Let's say for student 2 it's about 80, he has got 85, and this one he has got 89, and so on and so forth, right? For 10 students, right? And let's say that the last one got 91 over here, 90 over there, and got around 92 over here. He's a good guy, so he got that. So so we got this thing. So what it means that there are three values, right? So there are three rows for every student, and every column, right? So there are 10 columns, right? Represents one student.
Each column represent one student, and that would be S10, the last one.
Yeah. So that's sorry. Yeah, that's the 10 columns. So for every row, so we sort of write this whole thing as one matrix. This is what you'd call a matrix. You could almost see that this is made up of sort of like attaching all the vectors, individual vectors together, right? So we could say that it's like ps1, right? ps2, ps3. We sort of append them side by side, so each of them gives off a vector, right? We know this, as we've established. We sort of write this as a vector, right? And we say we sort of just attach them side by side. We don't want to write so many brackets all at the same time. We sort of write 71, 87, 91. We write this 80,
85,
85,
89,
89, and then we have 91,
90.
91, 90, 92. We sort of have all of this. We sort of write them together we combine them into one whole matrix, which is three rows and 10 columns, or this is also called a 3 by 10
Matrix.
matrix, right? This is basically a collection or a set of vectors. We want to store them all together, right? So okay, that seems nice. That's a notation, right? So please remember, these are all notations. These are all a way of compressing information. We want to talk about many things at the same time. I want to take the least amount of space to say so. So we're going to say there are three aspects or three dimensions of this piece of information about academic performance, and there are about 10 students. So we're gonna have a 3 cross 10 matrix where we're going to store the academic performance of three subjects of 10 students. This is what we mean when we give this whole matrix to somebody. So this is a compressed piece of information, right? Okay, moving on. How do we?
So Debayan,
Yeah.
can you tell me how can we represent the information regarding physical properties? Like, how
Hmm.
can we
So
relate it?
yeah, let's come to something more practical, more something that you will be working on frequently when you're working in data science, computing, machine learning, and quantum computing. How do we talk about physical quantity?
Hmm.
Right, like as in from physics, where we have a solid tangible thing, and it has a measurable property, some aspects of dimensions of it, and you want to measure those values, and want to store those values, sort of represent that quantity, right? Let's give a real example. Let's talk about space, right? What do we mean by space, right? So it's the same space that Einstein talked about, the same space that you live in, that we live in, right? So this is space. This is our world. This is where we live in, right? So how do we define space, right? So how we define the world that we live in using three pieces of information, right?
Okay.
So we define using three pieces of information. These are dimensions of our definition of space, right? Aspects, properties of space. What do we call them? We sort of denote them using shorthand notations called by letters, algebraic letters, x, y, and z, right? If you have taken a high school class in physics or maths, you should be knowing where we are getting onto this, right? So x, this first variable, right, which we call x, will contain the value of the information about moving, about the position, right? The position in the left right kind of direction, right? So if you're standing on a line, you want to go either to the left or to the right, right? So and you are at a particular value. So this is, let's say, some value 10. This is, let's say, some value minus 10. And then somewhere you have a zero over here. This is almost like a number line, right? So you want to go left, you want to go right, you want to stay somewhere. So that value, that position of your position in a left right fashion, in a left right property value or dimension, would be x, right? And we call this the first dimension of space. So y, the second dimension of information. So we call that movement, that space, a movement in space, where we talk about moving from front to back, right? Let's say this is the middle, this is 0, this is 10 minus 10 behind, this is 10 forward, so this is forward, this is backwards, right? So when the position where you are on this way plane of movement, this direction of movement, or this um, dimension of movement, is called the y value, or the location value along the forward back plane, and we call this represented using the y symbol. This is the y dimension, the second dimension of space. The z dimension is the other alternative, which is the top down.
Debayan,
Mm-hmm.
just a second before the z dimension.
Mm-hmm.
If x dimension is moving left to right, okay.
Mm-hmm.
So if I am standing on the line, I can move to front and back. That is also equivalent to x. Why we need a y dimension then?
So here's the thing, right? So if you combine x and y only,
Hmm.
right? So what do we get? We move front to back, right? Please forgive my drawing. Trying to draw a 2D plane on a 3D surface. So we have left to right, right? And we move front to back,
Hmm.
right?
Hmm.
So what you get is something like this, right? So your plane of movement is along this line for the x-axis,
Hmm.
right? So this is x, and you play the movement for y would be along this direction, right?
Actually, why do we need y? Is there any significance that we need y?
It is a piece of information, it's a piece of the puzzle, right? We are trying to find out where you are on space. What is your space? Where you are in space in this location? So we want to find out your location in space, and to do that, we need three pieces of information. We want to know where you are in a left right fashion. We want to know where you are in a forward back position. So if you intersect at least those two pieces of information for now, what you get is a grid. It's like a flat grid, right? So this is y, this is x, right? And we know that this one is the left right motion, right? And this one is the forward back motion, right? Combining these two, we could have one piece of information, as in where you are in the xy space, right? So let's say you are over here at 10. So this is 10. You are over here at 20. And both of these intersect as 0, 0. So this is 0, effectively. This is what we call origin, or the starting point, right? So we are 10 to the right of the origin 0, and we are 20 to the back, sorry, to the front of 0. So this one is negative, right? So this is 20, this one is a negative side of thing, this one is a positive side. So we are in 20 for front of origin, and 10 to the right of origin. So how do we represent that information? We combine those two pieces of information and we say, right, we are at this point in the xy plane. This is how we call 10, 20. Is this something similar to you guys? You might have seen this. This is the plane. This is the Cartesian plane. This is what we call the Cartesian 2D plane. And you might have experience working with this, and at least seen a graph paper where you sort of have xy directions. You plot points on it using this system. So what does it mean? It means that you can combine where you are in the left right plane, in the front to back plane, and combine them to give a more dynamic representation where you are in a 2D space, where you can move in all directions over here, allowed by a combination of all of this, right? This is your flat spaces. Now, let's make it more interesting. Let's talk about adding the z plane. The z plane is where you go about from top to bottom, that dimension, right? So if you include this in our 2D plane, right? So we have our 2D plane over here, right? So this is y, this is x, right? And our origin is over here. Oh, when we talk about the top to bottom, we have this is the z direction. So let's say this is the positive, so this is the top, and this is the negative z, right? Please remember the signs are a conventional thing, right? So if you choose that this is plus and this is minus, it's still okay. You just have to like represent your points differently. But what matters is we set with one convention and we just stick with it, just for the sake of everyone can understand. We stick with the convention, but remember, these are not set in stone. You can flip them if you want to, right? It would just mean the separate thing. It would just mean this plus minus setup in reverse. So it doesn't matter how you set it up. Okay, moving on. So z is a top bottom approach, right? So let's say you are at this plane. So this is 10, 20. You are on the xy plane, right? If I add information that given that you're 10 units from the origin to its right, you're 20 units in front of the origin, right? And then you are 5 units on top of the origin. If you combine all of these pieces of information, what do you have? It's a 3D space. This is, we represent this by 10, 20, 5, right? So this is your space, this is your location in a three-dimensional space. This is dimension 1, this is dimension 2, this is dimension 3, and this is your 3D space. Can you see the similarity of this information, right? This information with what we have discussed in the very first slide, right? Just some pieces of values, some pieces of information, which when combined represent a combined variable, some metric, some physical quantity, which is our location in space, right? Let's say you're sitting in your room right now, you're watching from your cell phone, you're watching from your on your computer, on your computer device, right? You're sitting somewhere, right? If the corner of your room, or where your door is, right, wherever it is the origin, right? You have three values that will exactly define where you are in your room or wherever you are in the world with that origin point, right? So you will have a position from the origin in terms of left right, where you are with respect to left or right of the door, where you are in terms of front or behind of the door, and where you are in front of, like in with respect to top or bottom of the door. Like I believe, like in your case, it will be 0 for top and bottom, because you are at the same level as the door, right? But consider if your origin, right, if your origin was somewhere else, so your coordinates will change. So your coordinate system depends on where your origin is, right? So 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 given a point, right, given a 3D space, right, think of this as the corner of your room. You have the x, you have the y, you have the z. These are the plus positive directions. I'm only talking about the positive directions. So the negative directions will be x of this will be minus x, this will be minus y, this will be minus z, right? And you are somewhere over here, which can be traced back to the origin, right, to your position, as a combination of x, y, z, three pieces of information. So we can encode your pieces of information space, right, your space position, as a vector x, y, z, right? So so this is a vector, this is your space vector, this is your location vector, you can call it. It's a vector, but you call it a location. It gives you location information. So this is your location vector, right? Now consider that there are many multiple things that you want to measure your location for, right? You have one thing over here, you have one thing over here, one thing over there. You have multiple vectors, multiple items to maybe find their positions of with respect to a common origin. So what do? You sort of put them in a matrix, right? So the our vector will be over here, x1 y. Okay, let's clean this up. X1, y1, z1. This is your item 1, right? So this is x2, y2, z2. This is your item 2, and so on and so forth. So many objects. So xn, yn, zn. This is your in, and this whole matrix can be your set of positional matrices, positional or location matrix. Just like a set of vectors. It's almost it's the same as what we discussed before with student marks, right? We sort of group them together, call them as one thing. So we can say the positions of all those 10 objects as this, and this is there are 3 dimensions, so we call this a 3 cross n matrix, right? And like before, this is a 3-dimensional matrix. There are 3 pieces of information, 3 properties of every piece of every piece of like value. Each of this is a one vector, right? So there are 3 pieces of information, and there are n of them, and we store them together in a 3 by n matrix. So I believe as of this point, you now understand when we say something is a vector, what do we mean? We mean something that looks like this and has some properties in it, and the number of properties is equal to the dimension of that vector of that property, right? And there are like and a matrix is essentially a set of these vectors, right? Just place one of the other and call it a set of vectors, right? This is what a matrix is, this is what a vector is. So now that we have cleared, like have a basic understanding of what are vectors,
Can you zoom a bit? It's like I'm
yes,
zooming in.
vectors and what are matrices. So as of right now, we should be comfortable with the ideas of vectors, which contain some properties and in a notation, in a way we decided to represent that information of a physical quantity, and we have matrices, which are nothing but a set of vectors, like collected together to represent properties or multiple instances of that physical quantity, right? So these are numbers, right? We store numbers in them most of the times, and it means that we can perform some kind of operations on them. We can add them, we can subtract them, right? Let's see how it looks like. So let's say we have a vector v1, right? We have three quantities in it, 1 2 3. We want to add it to another vector v2, which has 2 4 6, right? So how do we do the addition? We just add them element wise. We say 1 plus 2, which is 3, 2 plus 4, which is 6, 3 plus 6, which is 9. So the resultant vector v3 would be 3 6 9. Please note that the dimensions has to be the same. So this is three dimensional, this is three dimensional. So that means we can now add three dimensional objects, we can add three dimensional vectors. So it's not possible to add 1 2 3 and 2 4. It's not possible to add this. It's not even possible to add something that's beyond its scope, like 2 4 6 8. This is also not possible, right? So please make sure that whenever you add vectors, they have the same dimension. You could also do the subtraction on them, right? So you could have 10 9 8 subtract from 7 6 5, which is equal to 10 minus 7 is 3, 9 minus 6 is 3, 8 minus 5 is 3. Right, so we have a triple three vector.
Great.
Yeah, it's just the numbers that I chose. So we can do subtraction as well. Now multiplication is a bit odd, right? So what do we mean by that? I mean, so if you have a vector v1, right, 1 2 3, and if you have a vector, another vector 4 5 6, right, we can't multiply them like this. Now there is a reason. So this thing is, there are three rows. Like if you consider this a matrix, right? Like if vector is like a matrix with just one vector, we could technically think of like this, and this one would be the same, right? So the way it's defined is that matrices can, like vectors can only be multiplied. Okay, so 3 cross 1, right? So vector 1 can be written as a 3 cross 1 matrix, right? Because there are three dimensions, that just one vector, right? So that's a special way of writing vectors as if they are a matrix, and the second vector is 3 cross 1 as well. Now the way it's defined is 3 cross 1 cannot be multiplied with another 3 cross 1 vector. And the reasons for this, we're going to be talking about those in the next video, because we need a better understanding about another concept called linear systems. But the way it works, right, just for the sake of knowing it right now, is we can only multiply them if the number of columns in the first vector is equal to the number of rows in the second vector, right? So this two has to match for them so that we can multiply in the first place. We have to check this, and this is being called a vector 1 being conformable. That's a term. It's conformable, not comfortable. It's an N, right? It's being conformable with v2, right? So we have to check if this is works or not. Here, if we have a vector like 1 2 3, which is a
Yeah.
3 cross 1 vector, and if we write our second vector like this, right, which is a 1 cross 3 matrix, sorry. So this one is not the same as, like the one that we wrote in this vertical format. This means that this is a one dimensional vector So it's a one-dimensional vector, and there are three of them. So please keep this in mind. These are three columns, so there are three vectors, and each of them contain only one property. While this one there is only one vector, and that single vector has three properties. So these do not mean the same, right? Please keep this in mind. So when we have a product multiplication because between these two configurations of matrices or vectors, right? So these two match over here, like we said, these two are conformable. So we can perform this multiplication, right? And the result of this multiplication will be either a matrix or a vector. And how do we know that? We can only know that by looking at the other two values in their dimensions. So the number of columns in the vector one matches with the number of rows in the second vector, right? So that's a principle of conformability. So these two can be multiplied. What will be the dimensions of the resultant matrix? So it will be a 3 cross 3 matrix, right? So how do we do that? So how do we get this 3 by 3 matrix? Like we said before, the way that we get this is a bit complex, and we will be discussing about this more in detail in our next video where we talk about linear
Yeah,
systems.
that will be easier. I think that will be much easier because it's like that concepts which you learned today is too much for all of us.
So we're gonna leave that for the next video, right? So just for the sake, like if you guys want to know the answer, it will look like this. The answer is 4, 8, 12, 5, 10, 15, 6, 12, 18. So this is what the 3 by 3 matrix will look like, right?
So I think our audience can guess the answer, but let's see. We'll be seeing it next week when we understand the linear system of equations, because that will play a lot of part in multiplying vectors and all.
Yeah, definitely. So
And we
we're gonna
have
leave
some
that.
properties of vectors also, associativity and all. We'll be discussing each and everything at the beginning of next class.
Yeah. So let's move in on, right? So division, we don't have that concept of division in vectors. It doesn't make sense to divide properties of numbers by something else, right? But you do have the concept of like multiplying or like dividing a vector, right? So 10, 15, 20 by a single number. So you might add a number, like you might divide a number like this. So if you want to divide the whole vector by 5, so what you do is multiply 1 by 5 with this. That's essentially what it is. And this translates to, so 1 by 5 into 10, it is 2. So this will be 3, and next will be 4, right? So for single digit, like single digit division like that, it can work, but the vector by vector division is simply not defined, and it doesn't make sense to do that. It's just like infinity and division by 0 by 0. Some of them do not make sense, and therefore absurd values are not undefined. That's what it is. So the last part of this video is going to be talking about a special set of vectors or matrices, right? There is a concept called space, like not that space that we discussed, but a concept of a set of vectors which follow some properties.
So guys, that's what we discussed, Debayan, today. So we
Mm-hmm.
discussed about vectors, then matrices,
Mm-hmm.
then we talked about space, and we saw a few operations which we can do on vectors. And the next day we are going to talk a lot more about it, and we are going to talk a bit about Hilbert spaces, if I'm not wrong, and linear systems
Mm-hmm.
also.
We're going to talk about how do we expand upon those concepts of vectors and matrices. We're going to give more clarification on the multiplication operation if you guys are not clear on that, and we're going to expand into a whole concept of the things that is crucial for you guys to sort of move on to the next year of understanding machine learning and quantum computing ideas and concepts.
So, guys, that will be all for the day. Thank you for staying with us for so long. It was the first video on vectors and vector spaces. The next one will be on linear equations, Hilbert spaces. So stay tuned for the next week. So I was your host Shubro and
This is Debayan.
signing off. Bye bye.